This is going to be a slightly unusual talk, so I'm hoping the audience will participate. I've got some post-it notes, so if you have an idea, just shout it out. I'll write it down and leave it over here, and you can come back and decide what to do with it later on. My passion is technology and how we can use technology to make life better for patients, but also how to make life a bit easier for the people who provide the care to these patients. And so I'm fortunate in that I live this double life, two kind of highly interconnected but also somewhat independent lives, where on the one hand I'm a practicing clinician and I live the problems that we all struggle with every day. But on the other hand, I run a startup that is developing some AI solutions that is, in a very selfish kind of way, just try to solve the problems that I struggle with. And hopefully that will be helpful for patients, but also for the clinicians. What I'm going to talk today is my own opinions, I should add. So, but I'm just putting that up there as a disclosure. So there's a lot of hype around AI. I'm going to say that I don't actually know what AI is. AI, so we'll call it AI. It's essentially is a toolbox of techniques and methods that one can use to solve very complex problems that potentially one would struggle with to solve in the kind of more traditional statistical approach. That doesn't mean to say I'm not knocking statistics. I'm just saying these are different tools that are used in different ways to solve a problem. The problem is that there is a perception that AI is going to solve everybody, it's going to solve all the problems, and it's going to put us all out of work, and so it'll all just be, patients will be fine and none of us will be needed anymore. I don't think that's actually realistic. The reality is that we need to break down every single problem that we are dealing with into very many small problems and fix those one at a time. And so I think that when you hear people talk about AI, be interested, but be also slightly skeptic in terms of understanding what they're actually talking about and what they're proposing to do. So this session is about optimized patient care or precision medicine. I've just put this here to give us some sort of orientation in terms of where I'm coming from, or where I think we should be coming from when we think about precision medicine and how AI can help. And I think, again, the idea is that we need to break this up into bits. Precision medicine, as it says, it's you tailor the treatment to the individual patient. And actually, we do that already. We do our best every time we stand there by the bedside. We try to make a decision for that patient based on our kind of experience, our collective knowledge, our biases. And the idea that is that we further kind of try to find within this homogeneous bunch of patients that we are presented with, to find those that are similar in terms of their susceptibility to a disease or a condition, in terms of the biology or the prognosis of that condition, and also in their response to treatment. And I would argue that AI or machine learning or deep learning or that toolbox is very well designed to help us achieve exactly that. The problem is, this is where the problem starts. If you look at the literature, and it's actually this literature is quite good to review because there isn't a lot, and most of the studies you'll find probably goes back 1 year or maximum 2 years. And so this is a new evolving area where the publications are now beginning to appear, and with that I mean publications to do with in the kind of critical care environment. So if you were hoping that I'm going to show you all the papers that have been published about AI and optimized respiratory support, then you're going to be disappointed. So the question, though, is what do we do? So I'm going to show you some papers that have been published, not necessarily in the respiratory area, but this is why I brought the post-it notes, because I'm hoping that this is going to stimulate some ideas, because I can guarantee you that almost every single idea that you'll come up with, and almost any single question you have that you wrestle with, where you've stood and you've said, but there must be a better way to do this. I can almost guarantee you, with the right circumstances, the right data, the right approach, you could probably solve that problem and make to inform the decisions that you make for that patient. We just heard the previous speaker gave us an excellent presentation on ultrasound, and there was an algorithm with what you see, the curly bee lines and all the rest of it, and at the bottom there were the classes like pneumothorax and all the rest of it. Those images, you can train a neural network, a convolutional neural network, which is designed to assess and analyze images to classify the images for you into one of those. And so that begins to potentially give you some opportunities as to how you can either do something better for the patient or how you can improve the workflows to help you guys and me deal with the onslaught of patient numbers and expectation. This is not going to get any easier. The world is short of medical staff of all colors. I'm not a physician-centric speaker. We're all in this together. So we need to find ways to do this. So what I'm going to ask, if you're brave enough, if you have an idea, just feel free to interrupt me. Just say, what about this? What about this? I'll try and write them all down. I may keep an eye on the clock as well. And then we see what we come up with. And I'm going to just ask some questions as we go along, as we look at some of the publications. So this is a recent, is there anybody who want to make any suggestions already? So this is a recent publication, a systematic review, where the authors looked at papers published in the literature, in the critical care literature, where they've only used the clinical information system, so your Centricity or the other ICU management systems, and using that information to do research. And it's interesting because it begins to give us a hint of where the research activity is at the moment. And so what I'm thinking is that the list of do I have a pointer? The list of areas where the research is happening on the left can give us some ideas as to what it is that we can do in terms of ventilation management of patients. So if we say, that it says that almost a third of the patients of these studies are looking at predicting complications. There's a high number of papers predicting mortality. Can we improve prognosis? Already there's questions in my head in terms of, there's some things that we could potentially do in the ventilation area, alarm reduction, classification of subpopulations. This is interesting, just to point out that already there are, at the bottom in this column here, you can see there are six studies where the data set includes between 100,000 to 1 million patients. So this is most of those are within the last 2 or 3 years. So that's the direction. These data sets are now becoming available where we can really dig in. We have the volume of patients to help us, answer some of these questions or find some of these opportunities. So harm. Let's think about harm. We've known for 20 years that, longer than that, using too many tidal volumes or too high tidal volumes is bad for most patients. So surely there must be a way to work out how can we identify those who may be at higher risk of ventilation, of barotrauma, those who may be at lower risk of barotrauma. for me, more importantly, is there a way we can build this information and real-time monitoring with all this data that's coming from the ventilators and all the clinical information systems into business analysis so that we know what's going on in real time in our ICU, not just at the individual patient level, and we can train AI models to alert us of patients who are drifting away from where we would expect them to go, but also to tell us in real time at a system level what is in the respiratory environment, what is the quality of the care that we are providing to these patients. I don't think it always is just about the one patient, it's also about all the patients. You have to understand how your system performs. And actually, I think different hospitals, different ICUs, different systems will have different kind of performance sweet spots, which is a reflection of local practice, the population, and the diseases they see. So these are all things that we can begin to, rather than see it as a multiple kind of homogeneous soup, we can begin to kind of pick it apart and provide this information in real time. We can train models to give us information that's actionable in real time. I would find that very helpful. Who would find that very helpful? There's a few people there. The rest probably have this stuff already. Let's look at prediction in real time, prognostication in real time. So this is a study published by Ari Erkol and his team. They looked at, so we all use Apache 2 score to say we collect a bunch of stuff on the first day, and then we say, based on Apache 2, the risk of death for ICU hospital is X. Surely there must be a better way to refine that in that we know that as time goes by, we by the bedside begin to develop a better sense of whether the patient's going to do well or not. So they've shown that different types of machine learning approaches, not only on day one using day one data similar to Apache, are better at predicting the mortality. They can also, by collecting data as time goes by, refine the risk of death. And the interesting thing here is that they, in the machine learning models, they don't use the chronic morbidities that Apache use. They only use the physiological stuff that we have. So clearly they're already beginning to pick up within the population as a whole who the ones are based on the physiology, who's going to do better and who's going to do worse. The deep neural networks tend to do better here. I may say a few more words about these neural networks later on. So the question I'm asking, are there opportunities, what are the things that we would like to know that we think in terms of the ventilation management of the patient are prognostically important, maybe not just for mortality, but how we get how can we get people off the ventilator, who are the ones who are at risk, who are the ones who are at risk of a prolonged mechanical ventilation episode as time goes by. This uses real-time data as it comes in. What about individual patient level responses? So how do we know what can we figure out if I turn for an individual patient without having to do all the really clever stuff like imaging and all the stuff that people get up to, which has a definite value, but by just learning from thousands and thousands of other patients, can we make a prediction for the individual patient? Let's say if we turn the pressure support up, or we turn the PEEP down, or up, or whatever it is, change the mode from one mode to the next. This is an interesting study. Again, it's not respiratory, but it is in hemodynamics, children with sepsis. And what they've done here is the algorithm has learned to predict if I turn the vasopressor dose up by a certain amount, by how much does the heart rate increase for the individual patient. So this doesn't give you an aggregate probability of so many patients in the similar situations, blah, 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 all the rest of it. This tells you for this patient, given what the model knows about the patient, this is what the response is going to be. That to me sounds like an opportunity for AI in optimizing ventilation. And it may be that it goes counter to what we expect. This group has done is use a neural network, which is a recurrent neural network, which is a fantastic architecture for handling time series data. And so this is already now, when you're on your phone and you get predictive text or predictive words, it's an LST, a recurrent model that's predicting what the next word or the next letter is going to be. Because it turns out language is a time series problem. So these neural networks will remember the sequences of numbers and make predictions based on that. They're very complicated animals to play with, and they're computationally very, very challenging. What about can we predict how long patient is going to be on the ventilator, or those who are at risk of being on a ventilator for a long time? This group has done that. It's work in progress, but it's possible with a relatively high degree of accuracy to predict whether somebody early on. Sorry, let me say that correctly. It is possible to predict early on with relatively high accuracy whether somebody is going to need prolonged mechanical ventilation or a tracheostomy. So again, you make of this what you want, but the point being it can be done. It's possible to use data now, static data now, to predict something in the future, or even time series data that happens in real time. And that, by the way, includes text, which, as I said, is purely a time sequence problem. To make predictions, you can build text into models to make a prediction. For me, this is a really interesting. Those of you attending the various tech sessions and the tech lounge will hear about this study. This is a very important study published in Nature Medicine by Matthew Komorowski. So what they've done here, again, this is hemodynamic management in sepsis. But hold that thought, because we'll come back to that in a moment. What they have done is use reinforcement learning to understand what is the best way to manage to balance fluid and vasopressors in patients with sepsis. Reinforcement learning is learned like a game, in that you may have seen this in the media with DeepMind and Google. They play Go. And those are all types of deep learning, where the machine learns what the optimal strategy is to win. And so in this case, the machine will have learned the optimal balance for an individual patient between fluid and vasopressors. Now, on the left-hand side, they developed the model using the MIMIC dataset, and on the right-hand side, they validated it using the EICU clinical research dataset with about 200,000 patients. And it turns out that when the clinicians did what the model suggested, those patients did better. When they didn't, the patients did worse. So the point of this is that you can train using more data and more exposures than any one clinician, than all of us in this room together will have in many lifetimes. The AI can learn from that volume of decisions and begin to make recommendations for individual patients. Is this possible in mechanical ventilation? This is a group that has done this, used reinforcement learning to help with weaning individual patients from mechanical ventilation. And I've just put this slide on because what this also helps you, apart from just helping you to decide what to do or what combinations of things to do, you can also kind of work backwards and learn from the model. What are the things that weighs very heavily when it makes these decisions? So what are the really important factors that determine the success or the winning? It's fascinating. In this case, I mean, we would look at that list and say, yeah, we get that. But the point isn't that. The point is, this is one example. We can train, models to do, or to try and, we can try to train models to do almost anything. But you can increasingly now, and this is bleeding edge type models where you can have transparent models that tells you why this is the decision I'm making, or this is the prediction I'm making, and here's why I'm making this prediction. So the idea of it just being a black box are beginning to change. I've just put this one in because I mentioned text earlier on. So these guys used, again, recurrent neural networks, in this case a beast called a long short-term memory neural network, and they looked at all the physiology data in the ICU, and they looked at all the text, and they trained it to using the ICD codes as labels to be able to work out what the diagnosis is for the patient. So you feed a bunch of data in it, and it tells you this is the diagnosis. This is obviously an experimental setup where you have the labels, because you know what, at the end of an ICU stay or a hospital stay, the ICD codes get labeled, and so you can use that to train the model. But the point being is these models can read all your data and help you find diagnosis or patterns within the data that you may be helpful. Finally, how many people have pulled data from their own ICU database, and then you realize you don't actually know what ventilation mode the patient was in. You don't know when it was changed over. You don't really know what's going on, hour by hour in terms of what's being done with the ventilation. Right? Here is a group that have done. They fed all the ventilation, all the signals and the waveforms from the ventilator directly, and they've trained some models. And this is still work in progress. They've trained models to just distinguish between the different ventilation modes. So by having the model sitting to listen to or look at the waveforms, it can just clock for you or tell you this is now APRV, this is pressure support, this is CPAP. It sounds, we say, yeah, so what? But actually, when you're setting up systems to automate and to begin to bring in robotic processes into your workflows, these are the kind of bits where things will fall down if you can't automate what's going on. And you don't want to be dependent on somebody waiting for somebody to type it into the system to say it's now pressure support or it's now CPAP. I would argue that we're doing this at the moment because we have to, but I think that's a really stupid thing to do, because why would I want to have somebody, a human, type stuff into a computer when a computer can just do it for me? So I did refer to some of the neural network. Here's just a bit of blatant self-promotion. My colleague Adrian Georgievich and I wrote a very short introduction to what goes on under the hood in a neural network. So if you want to know more, I could suggest that as a good place to start, just to give you a brief introduction of what happens under the bonnet of a neural network. I'm going to finish with this, because I think it's as a geek, it's fabulous to be playing with this stuff and sitting there with a computer and data and coding and seeing all this stuff happen. But there is a reason as to why we're doing this. People have different motivations. For me, there are two main reasons. Number one is that we have an opportunity here to make things better for patients in a way that is unprecedented in medicine. That might sound somewhat dramatic, but I do believe that this is an unprecedented. As this types of technology has disrupted almost every other industry that we know, the same is happening in medicine. So we have to be ready for it because it will disrupt the way we do things now, for the better. And secondly, I think that there is an opportunity. The people who provide the care are struggling and buckling under the workload and the expectation, the demand, and are confronted with digital systems that are, in my opinion, not fit for purpose, not fit for human consumption. And so we need to find better ways to do things that doesn't require a human to do things a human doesn't have to do. So, in the words of Steve Jobs, on this hand we have biology, on this hand we have technology. These two things are now coming together, and we will build layers of information, much like Google has done with Google Maps, and they use different types of information that they layer on top of each other, and so you get the information you want, but it also gives you the depth of knowledge that you can drill into, that lets you build a complete picture of the patient. And that will obviously be data heavy, and in terms of, you can imagine if you were to take the data for one of the patients in your ICU, and you take their clinical information data, and you put all their imaging together, and they've also had some transcriptomic work, so they have some omics data done, and you put all that together, you can see how that becomes a massive, and if you multiply that over thousands of patients, it becomes a massive thing. But that's now possible, and that's the way things are going to go. So to conclude, I think where we are, though, is we talk about the big picture, but actually we need to focus on the many small pictures, like David Hockney has done here. He's taken many, many, many small pictures of the same scene and constructed them together to build the whole. And for me, this is a wonderful analogy to where we are and how we need to go about this. We don't have the whole picture yet. It won't happen in our lifetime, but we can begin to focus on the bits and take small pictures and make them as good as possible, and over time build the whole picture together. Thank you very much.